So today I will talk about my result on volume pressure on ice peak and crystalline mean curvature flow. This is joint work with In-Wan Kim at UCLA and Robert Pozar at Kanazawa University. So I will focus on these two topics today. So I will briefly talk about an ice peak mean curvature flow, and then I will introduce our result as well as geometric properties. So an ice peak mean curvature flow is a geometric evolution equation whose boundary moves with a normal velocity v. And here v is given by psi of normal n and then minus kappa sub phi. And here kappa sub phi and n each denotes the ice peak mean curvature flow and the outer unit normal. And we have two more functions here, psi and phi. They are positively non-homogeneous and convex, positive away from the origin, and they respectively denoting mobility and NSP in this system. So I will give you some example regarding this. So we consider the volume preserving version of such motions. So here you see that we have additional term lambda, which can be considered as Lagrange multiplier. And this Lagrange multiplier infers the volume constraint. The volume of omega t is equal to the volume of omega 0. You can see like one brief example of this motion. So we have in Rn, we have omega t, and then on the boundary of omega t, this set moves with normal velocity v, which is given by the equation m above. So very first example would be the following. Phi x and psi x both are the absolute value function. So in this case, this phi and psi both satisfy the condition I mentioned earlier, positively non-homogeneous. And I should also mention that here, this NSP curvature kappa sub psi can be formally understood as the first variation of NSP parameter functional. I will give you later. And if phi is C2 away from the origin, one can verify the equation here. Kappa sub phi is divergence of d phi normal. And here, also this divergence is the surface divergence, and this is so-called Kahn-Hoffman vector field. So in the simplest example, phi and psi are both absolute value functions. In this case, the curvature is divergence of normal. That means this curvature is exactly the mean curvature, and this is v equals minus h. So if we add the volume pressure term here, then you see that as time goes, the union of two balls converges to a ball. And what happens if phi and psi are not the absolute value function, but it is, for instance, L1 norm? So in this case, as I mentioned earlier, this motion of set is basically the gradient flow of the following parameter functional. Parameter sub phi is the integral of boundary of omega, and then phi, and then dh and n minus 1. So in this case, one can see that the minimizer of this parameter functional is the rescale of the following Wolf shape, so-called Wolf shape. And in this particular case, if phi of x is L1 norm, then this Wolf shape is exactly a square, so n-dimensional square. So in this figure, you see that if the initial shape is the union of two squares, then it will converge to a square. So I can give you more examples. So for instance, if we have a dumbbell, then as time goes, in the isotropic case, phi x and psi x are both absolute value function that it will converge to a ball. And what happens if the dumbbell has really thin part like that, then as you may expect, it will converge to two balls instead of one. Similarly, if phi x and psi x are maximum of x1 and x2, then it will converge to either a square or two squares. Then the natural question would be, does the flow converge to an explicit shape as time goes? And this is open question, and I don't have answer for this question, but probably it will converge to a finite disjoint union of wolf shapes. And wolf shape is, I mentioned earlier, like that. So the isotropic case and also stationary case, it is somehow expected because finite unions balls with equal radii are the unique critical points of the Euclidean isoperimetric problem. So the main difficulty is topological changes. So in general, the flow goes through topological changes, so singularity can happen even in 2 dimensions. Even we start with smooth surface, we can have singularities. So there are some partial results. In the isotropic case, Huiskin considered convex surface, and he showed the preservation of convexity. And there are 2 stability results, either in Hilder norm and in Sobolev norm. In the anisotropic case and crystalline case, there are 2 corresponding results. So one is for anisotropic convex, and the other is for crystalline convex case. Then our question would be, are there any other geometric properties besides convexity that is preserved with the flow? So this is what I'm going to talk about now. So in the isotropic case, there is one result by myself and Inwan Kim. So we assume that our initial set satisfies some condition. So the first condition is it satisfies row reflection, which is can be understood as a stronger version of star-shapedness. And then the volume condition, we prove the following. So under this condition, we show that our set omega t satisfies row reflection for all time. And then we also show that this set uniformly converges to a ball. And as I mentioned earlier, this property can be understood as stronger version of star-shapedness. If the set satisfies row reflection, then it is star-shapedness. And then if it is star-shapedness and then satisfies some additional condition, then it also satisfies row reflection. So this is the isotropic case, and I will not talk about proof, but I will focus on isotropic case, and I will explain what will be the main difficulties. So here is our main result for the isotropic case. So we still assume two properties on our initial set. So G1, the reflection property, and then G2, some kind of volume condition. And under these 2 conditions, we show that there is a viscous solution. And this also preserves volume, and then this also satisfies the above geometric properties all time. So it satisfies as long as omega naught satisfies G1 and G2, omega t satisfies G1 and G2. And in particular, but the boundary of omega t can be locally presented as a graph of function that is uniform Lipschitz in time and uniform Lipschitz continuous in space. Sorry, uniform Lipschitz in space and then uniform Hilder continuous in time. So this is our main result for the anisotropic case. So before I explain the motivation and then the key idea of the proof, let me introduce a notion of viscous solution. So since we may have some singularities, we cannot just consider the classical solution. We need to talk about discrete solution. And here I use the level set formulation of the mean curvature flow and then define a notion of discrete solutions. All right, so the motivation of our result is well-known moving plane method. If the n-dimensional sphere has constant mean curvature, then it should be, maybe the other way, but the n-dimensional sphere is the only compact and connected embedded C2 hypersurface of Rn+1 with constant mean curvature. And the proof is actually probably, like some of you know, and interesting. So if we have a plane and then if you reflect this ball with respect to a plane, then you can see that the reflected part can be included in the original part. So this ball has a plane of the reflection symmetry in every directions. So this is our main motivation. So we wonder if we can make a parabolic version of moving plane method. So if we have time variable, then can we apply this method? So the good thing is, since we used a notion of discrete solution, we can apply the comparison principle in a half space, not the whole space, but in a half space. And we can show that, rigorously show that if it satisfies some kind of reflection property that is described exactly here, so the reflected part is contained in the original part, then this property satisfies for all time. And here, this operator I just mentioned here denotes the reflection operator with respect to hyperplane of partial omega. So in this figure, in the union of two balls, you see that if we have hyperplane and then consider left part of this hyperplane, so that is our H, and then reflect the yellow part, then the reflected one intersect with H is included in the yellow part. So this is our main idea. However, the problem is if our domain is not a ball, then you can easily see that this kind of reflection property does not hold anymore. So for instance, our wolf shape can be the stationary solution. But if the domain is a square, then it does not satisfy the property I mentioned earlier because of the part here. And also, if the hyperplane is too close to the origin, then also it does not satisfy the property. So that means we cannot consider any reflection operator, but we should consider a set of the reflection operators satisfying the following property. So whose normals are in a subset, and then this hype space contains some ball so that this partial H is not too close to the origin. So this is our main idea for the anisotropic flow. Okay, so under this condition, we can define a new geometric property called G1. So it satisfies the reflection property, and then whose normal is in some set P, and then we have some condition on also H. Okay, so this is our lemma. This can be held in general, not specifically for the mean curvature flow, but as long as we know that this set satisfies G1 and also contains some big ball, and we can show that this set has the archon property. Here means that we have interior archon and also exterior archon at every point on the boundary. So in particular, omega is a Lipschitz domain. So the proof is actually not hard, but let me just explain the main idea. So the proof is basically if we have enough P, then we can find a basis satisfying the condition. So like for instance, if our P is a set of 8 unit vectors like that. And these actually correspond to reflection symmetries of a square. And what we can do is for a given point x in the boundary of omega, find the basis for R2 satisfying some conditions. So these 2 conditions are needed because we want the hyperplane is not too close to the origin. Then use G1, we can show that all gray part here, so these are our cone I mentioned earlier, should be first of all, the interior cone should be included in omega, and then exterior cone should be included in the boundary of omega. So this is the main idea. And you see that in this proof, you may notice that we need like enough directions. So P should be big enough. So in practice, we need to assume the following assumption. So the set P, so in general, so P is a finite root system and satisfies. So we need because enough direction in this root system. So under this condition, we can prove the previous argument rigorously. And then we also need to assume the following. So this set is compatible with phi and psi. Okay, so these are like details about our setting and as well as our proof. So under this condition, so the G1 and then also G2, I just explained that this discrete solution also satisfies G1 and G2 for all positive time. So this is first of all because of the comparison principle, as well as the geometric property I mentioned earlier. So as a consequence, this set can be locally Lipschitz in space. So again, because of our geometric property. Okay, so that's all for today. And here are some references regarding my talk today. So, and also just for fun, there are some more examples. So like Pegasus to a ball, and then this to a square. And I heard that the mascot of the Kansas State University is this wildcat. So you can see what happens if we evolve.
That's really cool.
Yeah, I'm sorry not to include the mascot of Kansas University of Kansas, right?
Next year
Yeah.
you should do that.
Yeah.
Thanks a lot. That's a really cool talk. Any questions for Dohyun?